So July 17th, 2019. And see here are some problems from the two sections that we had, 2.7 and 2.8. Ouch. So number one, say let f of x be equal to the square root of, say, 1 minus 5x plus 1 over x. Find the domain of f. Number two, let f of x be equal to the square root of, say, 5 minus x squared and I want you to find f of two, like this, and number three, let f of x be equal to, say, 2 over 2x minus 1 and g of x be equal to, say, x minus 2 over x minus 1, so x plus 2, like this, x plus 2. Find f of g of 0. Okay. Number 4, let f of x be equal to 2x over 3x minus 5. I want you to find and simplify f of x. Number 5, let f of x be equal to x over x plus 4 and g of x be equal to 2x minus 1 over x plus 1. I want you to find and simplify f of g of x, like that. Sometimes they just put f of g, right? They don't have to put of x. It has to be a function of x. Number 6, let f of x be equal to, say, 2x plus 5 divided by, say, x minus 1. I want you to find a formula for the inverse. For the inverse of that. And number 7, let f of x be equal to, say, x times, this is going to be a challenging one, so I'm going to put a star next to it. And so if you can't do number 7, is fine, but if you get it, that would be great. So let f of x be equal to x times 2 minus x. I want you to find a formula, and where x is bigger than or equal to 1, find a formula for the inverse of f. So these are 7 questions. After that, we're going to do one more example, and then we will move on to that. We can take a look at the questions that they ask on the final exams, and see what is it that they're looking for. So we'll start going over these in just a few minutes, right? But for now, I'll give you like 5 minutes to see if you can finish copying them down and try to see if you can start off solving some of this. Today, our goal is to cover 3.1 and 3.2. 3.1 will be focusing on quadratic functions like parabolas and sketching them, and then 3.2 will be the polynomials and the graphs of polynomials, just a rough sketch of how will they look like and so on. Yeah. So I asked you yesterday in the meeting about the IDs. They said most of you should have taken a picture. So how many of you did not take a picture? Did not. So they say that they are waiting for an email from the ID office, and the ID office, like many offices, they only have one printing machine for the IDs. It's like they're gonna let us know when we can go, for those who haven't taken a picture, when we can go downstairs to take the picture for your ID, and then after that, then they will print the IDs, and we don't have to go and collect them. Someone will bring it to us, or they will give it to the TA, and we will distribute them out, right? Yeah, but just know that they are working on getting your IDs. Is it hard getting in the building, or no?
Not too bad now.
Not too bad. Yeah, that's fine. Yeah, sometimes they could be like annoying, or like, where's your ID? And then they take all of your information, like license or ID, state ID sometimes. Right. So for number 1, right? Let's start on this one. For number 1, let me push everything else down. For number 1, what will you say the domain of this function is? Anyone?
Negative infinity to 0.
And then from 0 to
It can't be more than 0. 1/5. Oh yeah, 1/5.
to 1/5. Do we include 1/5?
No.
Yeah.
Yeah, we do.
Yeah.
Oh,
Yeah. If the square root was on the bottom of a fraction, we wouldn't allow the 0 to exist, but because that's not a problem. So we'll go from negative infinity to 0. And we have to omit 0 because of the second part, right? The 1 over x. And then we're going to start from 0 again, and we're going to end at 1/5. 1/5, we got 1/5 from 1 minus 5x, right?
Yeah.
1 minus 5x, right? So this is the answer, but let me highlight this with this color here. That's bad. So we got the 1/5 because when we take a look at the inside of this guy, right, of the square root, 1 minus 5x has to be bigger than or equal to 0. That means that 1 has to be bigger than or equal to 5x. That means that 1/5 has to be bigger than or equal to x. So that means that x has to be less than or equal to 1/5. Right? So it cannot be more than 1/5. It has to be to the left side. And we omit the 0 because of the second part, right? The 1 over x. If x is 0, then the 1 over x will be undefined at x equals 0. But that's good. Right? What about for number 2? So let me push everything else down. Yeah. So f. So this is a composition, right? Let me do it with green. So let's start off with f of 2. Let's focus on the inside f of 2 first. What is f of 2? Yeah, f of 2, all we have to do is plug this into it. And what should we get when we plug this 2 into it? So that's going to be the square root of 4, which the square root of 1, right?
Yeah.
Which is 1, and f of 1 will equal to
5 minus 1 is 4.
yeah, so this will be the square root of 4, which gives you back 2. Yeah, so that's fine, right? And these will be the answer that we get for that. That the answer will be just 2. It turns out that when we take f of 2, we get 1, and then f of 1 will give us back 2, right? It's like a little cycle there. So if you start off with 2, 2 goes to 1, and 1 goes back to 2 when you compose it. And if you keep on iterating this, like f of 2, you will just throw in 2 to 1, 1 to 2, 1, 2 to 1, and 1 to 2. So yesterday, I talked to you about sometimes these iterations create a cycle, right? And this is one of those cycles that if you keep on iterating this, it will just keep throwing 1 to 2, 2 to 1, 1 to 2, 2 to 1. So, yeah. So what about number 3 for this one? Yeah. So let's push this down. There we go. So f of g of 0. What is g of 0?
-1.
Yeah. So this will be f of -1. And what is f of -1?
-2
Yeah. So it will be 2 divided by -2 minus 1, and that will be -2 over 3. That's it, right? If you had to simplify your fraction, like it was -4 over 6, you should be concerned on simplifying your answers. But because it's already simplified, like -2/3, that's fine, right? Just keep that in mind. But so that's for number 3. What about for number 4? Let's see. They just give you one single function and they ask you to find the composition of f with itself, right? So let's see. This will be f of x, like this. And f of x is 2x over 3x minus 5. And this is just going to be 2 times x divided by 3x minus 5. Well, what are we replacing inside of those parentheses? We're yeah, 2x over 3x minus 5 and 2x over 3x minus 5, like this. What should we multiply the 5 by to get common denominators on the bottom? We should multiply this by 3x minus 5 over 3x minus 5, right, like this. And once you get to that stage, do you see that the denominators are the same, so you can just ignore them, right? You can just cancel them out, all of the denominators. What are we going to get on the numerator?
4x.
4x, and on the bottom we're going to get
It's 9x plus 20.
yeah, 6. Yeah.
9x plus 20.
Yeah. So over here we're going to have 3 times 2x, that would be 6x. And then we distribute out the -5, right? Yeah, -15x plus 25, right? Yeah. And when we simplify this out, we have 4x in the numerator, and on the bottom we're going to have
25 minus 9x.
So that will be 25 minus
9x.
9x. There you go. And there isn't anything that we can simplify it after that. That will be it. Like this. Like that. Is f its own inverse? We'll say no. What will happen if f was its own inverse? You will get back x, right? f of x would have been just x because the input of the composition will just be the output. But this is not its own inverse. It's rarely the case when f is its own inverse. It's like, but it happens. Yesterday we saw an example where f was its own inverse, right? Yeah, but it's not always the case, right? It's rare to see that. What about number 5, right? Yeah, for number 5, I give you two functions and I ask you to find and simplify this composition. So it will be f of g of x. This will be f. G of x is 2x minus 1 divided by x plus 1. And f of that will just be what we have there. X divided by x plus 4. But we are substituting 2x minus 1 over x plus 1 into x, right? So it will be 2x minus 1 over x plus 4. No, x plus 1. And then the same thing here. 2x minus 1 over x plus 1. And what should we do first here? Multiply the 4 by
X plus 1.
over. And at this step is when we cancel all the denominators like this, right? And on the numerator you're gonna get 2x minus 1. And on the bottom you have 2x minus 1. And then distribute out the 4 in the second part, right? The second expression. What are we gonna get there? And let's simplify this out a little bit more. So we have 2x minus 1 on the numerator. And no, you cannot cancel out the 2x minus 1 over 2x minus 1. You can only do that if the bottom would have been a product, right, of two things. But we have to combine like terms there. So we have 6x. Yeah, plus 3. We could factor 3 on the bottom. It's not necessary. That's not the point of this. We can't simplify that anymore. And that will be the answer that we get. Are f and g inverses of each other? The answer will be no. What would we get if they were inverses of each other?
Same thing.
We would have gotten out the x, just an x, right? They would have canceled out. We call that the inverse property, right? For functions, and we didn't get x. We got an expression 2x minus 1 over 6x plus 3. And we're not concerned on finding the domain, but if you were finding the domain of this one, the last thing over there tells you that x cannot be negative a half, right? Because then the bottom will be 0. And you will also have to consider the input, right? The input function, g of x. So x wouldn't be allowed to be negative 1 either. So the domain for this one would have been x cannot be negative 1 and x cannot be negative 1/2. Yeah, but again, we went over that yesterday.
About negative 4 as well for F.
That's not the input function, that will be the output function, yeah. So if you were to do the other composition, g of f, where f will be the input function, then we will consider that, yeah.
Mr. What's the domain for number 4?
The domain for number 4, yeah, it would have been everything except that x cannot be 25 over 9 and x cannot be 5 over 3.
What about 0? X cannot be 0, right?
Sure, you can plug in 0. Yeah, you can plug in 0. Take the composition of that. And but again, I said that yesterday that we could write the domain of all of this, but it's not what you want to focus on. But if you want to write them out, you can write it like this if you want to. The domain for this one would have been all x in R, like this, such that x is not equal to, right, 25 over 9th, and x cannot equal to 5 over 3. And we took a look at two things, right? The result that we got from there and the input function. In this case, the input function was f itself, right, for number 4. And for number 5, we have this as a domain. The domain for this would be everything, all x in R, except that x cannot be negative 1 and x cannot be negative 1/2, like this. like that. And let's move on to number 6, right? So for number 6, they ask you to find a formula for the inverse of our function f. How should we do this, right? We did one example yesterday.
Set x equal to y.
So let me start off with this. Right? Y equals to 2x plus 5 over x minus 1. By doing this, we're saying that the output variable, right, is a new variable, and that will be the variable y. And the next step will be to switch the variables, the x and y's, right? So it will be x equal to 2y plus 5 divided by y minus 1.
Solve for y.
Yeah, and then we solve for y, right?
These are really easy questions, Mr. I did back in my junior year.
Sure, and again, it's I think most of us have seen it before. It's just that we're trying to put it together, yeah. And I mean, at the end, if you get to pass that final exam, right, you move on to 195, and but at least you have an idea of what college algebra is. Yeah. Okay. So we cross multiply, and we're gonna get this x, y minus x, equals to 2y plus 5, like this. And now our goal is to solve for y, the y variable, right? So let's see. If I subtract 2y on both sides and add x on both sides, I can end up with something like this, right? I can end up with something like this. And by me putting the y variables on the same side of the equation, I can now factor the y variable out, right? And if I do that, I'll get this. Like this. What? And on the right side, I still have 5 plus x. And finally, when I solve for y, what is that y going to equal to? Y is going to be 5 plus x divided by x minus 2. And that new y variable is what we're going to call the inverse function of f, like this. And this will be 5 plus x divided by x minus 2, like this. And this is the formula that we'll get for the inverse. We're not concerned with finding the domain of the inverse. But what would you say the domain of this inverse is?
Can be 2.
Yeah, the domain is that all x in R,
That can't be 1.
x cannot be 2. That's it.
Oh, it doesn't matter what the domain of the other one was?
Yeah, it wouldn't, yeah. Because we are not taking the composition. Yeah. And so this is the domain for that. Again, you're not responsible for finding the domain, but something that you should know on the back of your mind is this. Here's a little remark. Remark is that the domain of the inverse function of f is equal to the range of the original function f of x, like this. It's a little remark. And so when you find the domain of this inverse function, you ended up finding the range of our function there. Yeah. And if you want to talk a little bit about the original function f of x, it can be every y value that you can possibly think of, every y value, the range, right? Except for the y value at 2. At 2. The y value cannot be 2. Why does it skip the y value at 2? It will have a asymptote. And what kind of asymptote will it have? Horizontal asymptote. That's what the function will have. It's everything except for y equals 2. It hits everything except for that y value. And what about the vertical asymptotes? Well, you look at the denominator of the original,
One.
and that's 1. So it has a vertical asymptote at x equals 1 because x cannot be equal to 1. And now we know that it has a horizontal asymptote, that y cannot be equal to 2 by looking at the domain of the inverse. So it makes sense why the domain will be of the inverse will be the range of the original function. Sure, yeah. So let's go to Desmos, right? Desmos. And so f of x, yeah, it doesn't, we are going to name it f of x equals to, so what do we had on top? 2, yeah, x plus 5 over x minus 1, right? Yeah. And I'm gonna type or write two lines. One of them will be the vertical asymptote. We say that we will have a vertical asymptote at x equals 1. Yeah, at x equals 1. And the other one will be at y. The horizontal asymptote will be at y equals 2. And let's look at the graph now. And look. You see. Do you see that we will have a vertical asymptote at x equals 1, the blue line, right? That the function will always be asymptotic to the blue line, right? You see that? Right? Yeah, gets closer and closer. What about down here as well? Is asymptotic to the blue line, and that's vertically. What about horizontally? This is asymptotic to this line right here, and if you see, that's the line y equals 2, and it will be asymptotic to it like this.
This is one-to-one function, right?
Yeah, it's one-to-one function because if you draw any horizontal line, it will only cross the line once, not twice.
And it has to be crossed at only once, not twice.
The horizontal
Yeah.
line test, yeah. In mathematics, later on, we don't use the horizontal line test because you can't always graph these functions. So remember yesterday how we did this by using algebra? Yeah, I can do it for this one if you want to. Yeah. So let's do it for this one, right? Let's do it for this one. We'll say something like this, right? And this is not meant to be done in this particular problem, but we can do that here. And I'm going to ask, how do we know that this function is one-to-one, right? Let me just put a box here. Yeah, there you go. That's not what I want. Yeah, there you go. That should be a box. So, like, y is f of x equal to 2x plus 5 over x minus 1, a one-to-one function. The way that we do this will be that we say that we want to show that f of x1 is not equal to f of x2 whenever x1 is not equal to x2. That's what we want to show. It's a little thing. And what is f of x1? F of x1 is equal to 2x plus 5 over x minus 1. Let's make these equal to f of x2. F of x2 will be with the 1 here, and this will be 2x2 plus 5 over x2 minus 1, like this. So we start off with that. And we say if, we can do it not equal to it or equal to it is fine. It's, there you go. If these guys are equal to each other, okay. If these guys are equal to each other, we have 2x1 plus 5 divided by x1 minus 1 equals to 2x2 plus 5 over x2 minus 1. We cross multiply and we get this. I'm just going to do it step by step. 2x1 plus 5 times x2 minus 1 equals to 2x2 plus 5 times x1 minus 1, like this. Yeah. And now, at this step, yeah, that's better. Let's distribute everything on the left side. So we have 2x1 x2 minus 2x1 plus 5x2 minus 5. And on the right side, when we distribute this out, we'll get 2x2 x1 minus 2x2, right, plus 5x1 minus 5, like this. But do you see that these 2x2 x1 will cancel out on both sides? Because if you were to subtract that term, it will just cancel out on both sides, right? And the 5s will also cancel out on both sides, right? If you add 5 on one side of the equation, it will just cancel out the 5 on both sides of the equations. So what do we have on the left side here? Negative 2x1 plus 5x2 is equal to negative 2x2 plus 5x1. So let's group these together. Let me add 2x2 on both sides. So I'm going to have 2x2 minus 2x1. All I did was move the negative 2x2 from the right to the left. And what am I going to do with the 5x2 on the left side? Yeah. But I have everything on there. So imagine I have this plus 5x2, and then plus I think this is let's see, 2x1. So and then I'm gonna bring also on the left side the negative 5x1, like this. I put everything on the left side like this. I was gonna take the x1s on one side and the x2s. It doesn't matter. Can I combine like terms in this case? Yeah. So I move everything to the left side by adding the 2x2 and subtracting the 5x1. And by doing this, I can combine this, and that's going to give me 7x2. And I can combine the other two here, and that's going to give me negative 7x1 equal to 0. And I can move the 7x1 on the right side. And if I do that, I'm going to end up with this. 7x2 is equal to 7x1. Divide by 7th, and you get that x2 is equal to x1. So the only way that f of x1 can equal to f of x2 will be that if x1 equals x2. Consider this picture here. Consider this little picture here. Imagine that this is the function right here. Like this. Like that. Is this a one-to-one function? No, because here is x1 right here, right? And that gives you this value, and here is x2 right here. What is f of x1 equal to? Is the same value that f of x2. Is x1 equal to x2? No, where x1 is not equal to x2. These will fail off. But if I give you an image like this one right here, like this one, say this is my function now, like that. Is this function one-to-one? Yeah, because the only way that f of x1 can equal to f of x2, the only way that they can be equal to each other, right? So here is x1. There is no other value for this one, right? If I say, hey, there is an x2 and f of x1 will equal to f of x2, the only way that they can be equal is if they are here. That's the only way that they can be equal to each other. So if f of x1 equals x2, it is because x1 equals x2, right? The other one, if f of x1 is equal to f of x2, it doesn't mean that x1 is equal to x2. They can be two different values. But so this is how we show it mathematically, but you don't have to do this in a test, or I'm not going to test you on it, because this will require a little bit of understanding what do we mean by a function being one-to-one in algebraic in algebraic sense, right? And it would be that the two outputs can only be equal if the two inputs are equal, right? And for the first picture that I gave you there, that's not necessarily true. The outputs are the same, but the inputs are different, right? And you can even take a look at this in a little table like this one here. So suppose that the output here is y1 right here. So, and you say, hey, here is x1, here is x2, and where is x1 going to be going to? y1. And where is x2 going to go to? y1. So every time you have a little triangle, right, on the right side, you're mapping 2 points into the same y value. And that will create not a one-to-one property. Every time you have the little triangle, two inputs going to the same output, it fails the one-to-one property. But over here, if you do something like that, x1 is going to be mapped to f of x1, and x2 will be mapped to f of x2, but they're exactly the same point. Think about it this way, right? Suppose that there is a man in a cave, and every morning all he sees is the shadow of a bird, right, on the floor, and he thinks to himself, is it possible to reconstruct the body of the bird by looking at the shadow of it? And the answer for that one will be no, because many points on the bird are being mapped to the same point on the shadow. Like how can you reconstruct the body in 3D when many points on the bird are mapped to the same point, right? So that's exactly the case of the first one, where maybe a point on the head of the bird and a point on the body of the bird, like the belly of the bird, is mapped at the same point on the shadow. How can you reconstruct this backwards? How can you start from the shadow and know which point will go back to the head and which point will go back to the body? You cannot do that. That cannot be done. If you can do that, that will be a one-to-one property. If you go from a point to a second point, you can do that. For example, and this is out of this, right? Have you ever heard of a stereographic projection? A stereographic projection. I will erase this a little bit. So imagine that you have this, the shape of a